Hi everyone, in today's video we are going to be doing this problem right here, which is a pretty complex problem. This problem is telling us to evaluate the sum of 2023 choose 0 plus 2023 choose 3 plus 2023 choose 6 and so on, all the way to 2023 choose 2022. So just to rewrite the problem, we are trying to evaluate the sum of 2023 choose 0 plus 2023 choose 3 plus 2023 choose 6 and so on until we get 2023 choose 2022. So at first this kind of looks like a row of the Pascal's triangle. In fact, this actually is. If you know the sum of a row of the nth row of Pascal's triangle, if you were to take the sum, that would actually equal 2 to the n. And the reason for that we can actually show using the binomial theorem, because 2 is essentially 1 plus 1. If we had that to the n, applying binomial theorem to this binomial expansion, that would simply give us n choose 0 times 1 to the n times 1 to the 0. But I'm not going to write these 1 terms because 1 to any power is just going to be 1. So to save some space, I'm not going to write those. Now if we continue on, we'll get n choose 1 plus n choose 2, and so on. This is just a simple application of binomial theorem to show the sum. See here, this is a row of the Pascal's triangle, the nth row to be specific. And if you were to sum up each element, that would simply be 2 to the n. So now if n was 2023, that would basically look like this. And to expand it out, we would have 2023 choose 0 plus 2023 choose 1 plus 2023 choose 2, and so on until we get 2023 choose 2023. So this is great for us because this looks pretty similar to what we're trying to solve up here. However, clearly we are missing a few terms in between. It may not be obvious at first, but we are actually going to use cubic roots of unities to try and get rid of those missing terms. More specifically, in this video, we are going to be using the cubic roots of unity. So just for some quick review on what that is, if we had our coordinate plane here, the complex plane, the cubic roots of unity would satisfy this equation here, x to the third equals to 1. And that would look like this. You would have one root right here being 1. Then you would have another root, 2 pi over 3 or 120 degrees. And you would have another root over here. Again, these satisfy this equation right here. And it perfectly divides the unit circle into 3. So this is the first one, and we'll just have the second root of unity for the cubic be omega. And this is actually omega squared, because if you times two complex numbers together, you are adding their angles together. So omega squared would be over here because you've just added 120 degrees to omega. Now, we also have another property that is very important that we're actually going to utilize later. The sum of the roots of unity for some nth root of unity is always going to be 0. So in this case, 1 plus omega squared is going to be 0. These are all very important facts, and we will get to using them now. Let's erase this and get to solving the problem. This might seem kind of random, and there might not be so much intuition on why we're doing this, but it's actually very clever in solving this problem. So now we're going to bring in 1 plus omega to the 2023. And let's write this out using binomial theorem. We would start off of having 2023 choose 0. And then that we would have 1 to the 2023, but we're not going to write that. Next, we would have 2023 choose 1. And again, I'm just applying binomial theorem here. And then we'll have omega to the first power. And let's just keep going. using our knowledge of binomial theorem. So this is what it would look like, and just to be clear, I'm multiplying this to 2023, choose 2023. I just simply ran out of room. So now, how would we get rid of these omegas? Well, remember, omega satisfies x to the third equals to 1. So therefore, omega to the third is going to equal to 1. So anytime we see any multiple of 3 in its powers, such as omega to the 3 times some integer k, we can know that it'll just equal to 1. So that's that. But also, what if it was omega to the fourth power? Well, remember, omega to the fourth is simply omega to the third times omega. This here is 1. Now, if you multiply that by omega, remember from before when I mentioned that when you multiply two complex numbers, you add the angles. So if omega to the third is 1 over here, if you multiply omega, that would bring you back to omega. So omega to the fourth is essentially omega. Now what about something like omega to the fifth? Well, omega to the fifth is omega to the fourth times omega. And omega to the fourth is over here, as we just saw. So if we multiplied another omega, we would add the angles, and that would bring us over here, which is basically omega squared. So now we notice pattern. Whenever we have the exponents, when the exponent is congruent to 0 mod 3, we'll be given 1. When it has a remainder of 1 when divided by 3, like the exponent 4 here, we're going to end up back at omega. And when we have a remainder of 2 mod 3 in the exponent, we will end up at omega squared. So now this can help us get rid or simplify this crazy looking term. So let's first use this fact right here, that omega to any power that is a multiple of 3 is going to end up equaling to 1. So let me delete all this. Now, anytime we see like omega to the third, and eventually I did not write it out, but if you have something times omega to the sixth, to the ninth, and so on, those are just going to go away because they equal to 1. So let's really quickly just rewrite this. We'll have 2023 choose 0, and so on. I will just write this out. And here, our omega to the third goes away, so and then we are left with this. But remember, this 2023 exponent can actually just become omega to the 1th because of what we discussed earlier. So that is omega. Now we have cleaned up our equation a lot, and it looks like we are on the right track, because if you look at our original, this has too many terms because we don't want these terms right here, right? Well, we have them alone. We have this term alone, just like in our problem. So it seems like we are on the right track. Now, for our next step, we're going to bring in omega squared. So let's write the expansion for 1 plus omega squared to the 2023. Again, let's use a binomial theorem here. That'll give us 2023, choose 0, plus 2023, choose 1, times omega squared, plus 2023, choose 2, times omega to the fourth, and so on. And we're going to end up with 2023, choose 2023, times omega to the 4046. So I've actually changed the color to make this easier to look at. The pink colored terms are what we are keeping for now because we're going to use them later. So same with what we did before, we can simplify everything a little bit more so we don't have a bunch of crazy exponents. So this would essentially be 2023 choose 0 plus 2023 choose 1 omega squared. And for this next term, we discussed earlier that when it leaves a remainder of 1 mod 3, that'll just be omega again. And of course, if it leaves a remainder of 2 mod 3, that'll be omega squared. So let's keep writing this as just omega this time. And our next term, I did not write it above, but we know that it'll be omega to the 6th. And again, we mentioned earlier that if you have omega to some 3k, where k is an integer, that'll just equal to 1. So for our next term, it's just 2023, choose 3. And we can keep going till the end. And 4046 leaves a remainder of 2 mod 3. So we'll actually have omega squared for that last part. So we've simplified this a little bit further as well. So for now, we are done with the crazy binomial expansions. I'm going to delete all the white colored terms and show what we want to keep. All right, so I've just rearranged our terms so it is a lot easier to look at. We have just expanded all of these using binomial theorem. Now let's see what we can do with these three right here. What if we added them all together? That would actually help us a lot. Let's see how we would do that. So if we added all of this together, that would leave us with 3 times 2023, choose 0. Now this next part is interesting. You would have 2023, choose 1, times, and we have technically an invisible 1 here, right? So that would be 1 plus omega squared. Now, this is interesting because earlier we discussed that when you sum the roots of some nth roots of unity, that will always equal to 0. And these are our cubic roots of unity. So this sum equals to 0. Anything times 0 is simply 0. So this whole term will just be 0. Now let's keep moving on. Here we can see that it's actually the same thing. We have 1 omega squared and omega, which again, if you sum them all, that's going to be 0. So this term will end up being 0 as well. This is looking very nice for us. Let's keep going. This next term, we have no omegas because earlier we actually simplified them and got rid of them. So we would just be left with 3 times 2023, choose 3. We are definitely on the right track because this matches up with what we want. So it will keep on going like this. It will be 2 zeros followed by some non-zero. And for this last term, again, there's an imaginary, or I shouldn't say imaginary, I should probably say invisible. There is an invisible 1 there, and that term will end up being 0. So instead, for our last term, I'll just write the term before, which will be 2023, choose 2022. And there are 3 of those because we're adding all of these together. So this is what we have now, which looks exactly or almost exactly like what we're trying to solve for. But we still have these nasty 3's in the way, so let's see how we would do that. If we set S to be the sum of what we're trying to find, then here, with this entire thing, would be equal to 3S, which would also be equal to 1 plus 1 to the 2023 plus 1 plus omega to the 2023 plus 1 plus omega squared to the 2023. So this looks almost identical to what we are actually trying to solve for in the beginning, except we have some 3's here that we don't want. So let's see what we would do about that. You can pause the video right now and try to come up with how you would solve this, but if not, I will keep on solving this problem. So let's set S to be what we're actually trying to find. Then in this case, when we have added this entire thing, that would mean that 1 plus 1 to the 2023, essentially this is what we did earlier by summing the left-hand sides, plus omega to the 2023, plus 1 plus omega squared to the 2022 equals to what we have up there, or essentially that's just 3S. So now that we have this, how can we actually make this simpler? We certainly do not want to use binomial theorem again for these. Well, this first term is pretty nice. That's just 2 to the 2023. But what about these? What are we going to do about this? Don't worry, we do not have to use binomial expansion again. If we use this fact one more time, that 1 plus omega squared is equal to 0, we can actually make this a lot simpler.
So now if we look at here, we have 1 plus omega. So we can actually use what we learned before and manipulate it to get 1 plus omega equals to negative omega squared.
So we can plug in negative omega squared for 1 plus omega. So we have negative omega squared to the 2023. And let's just do the same thing for 1 plus omega squared. If we manipulate this equation over here, 1 plus omega squared is just going to be negative omega. So we'll write that in. Negative omega to the 2023 equals to 3 of what we are trying to find. So we are almost done with solving this insane problem. Now we can go even further using our knowledge of complex numbers to get rid of these and make them simpler. Well, this would just equal to this. So this is essentially negative 1 to the 2023. So an odd power would just make it equal to negative 1. So let's just write negative. And then we will have omega to the 4046. And same for here. We have to some odd power, which is 2023. So we're going to minus omega to the 2023. Now, let's simplify these even more using our knowledge of complex numbers. Remember, if it's mod 3, the remainder here is 2. So if it leaves a remainder when mod 3, that will equal to omega squared. So we're going to have minus omega squared here. Let's write this in as well. And now, for this final one, this mod 3 leaves a remainder of 1, so that will simply just be omega. We're going to use this fact one last time, that 1 plus omega squared equals to 0. Because for this part, if we were to subtract omega and omega squared on both sides, we would get 1 equals negative omega minus omega squared. So in this place, we can just plug in 1. Therefore, 2 to the 2023 plus 1 equals to 3s. Let's divide 3 on both sides. That would give us our answer to be s equals to 2 to the 2023 plus 1 all over 3. This is our answer. We have finally found the solution. Thank you so much for watching. Please like, share, and subscribe.